I'll start with a little introduction of myself. I am graduated as a physicist, and after that, I didn't do any physics work. I did a lot in ICT, but only after my retirement I got interested in quantum physics because it says something about consciousness. And this developed in courses that I gave for several institutions. And at the moment I'm giving the course I've also given to you at what I translate to the Academy of Spiritual Science. Only the course I'm giving you is much shorter than I gave there. They need 5 sessions. And during the sessions, I got a lot of complaints in the beginning. Why do we have to know all this technical stuff? And at the end, everybody thanks me. They say, now I understand why I need to know this. So don't be afraid, everybody. Everything will become clear. And I'm going to share my screen now. I don't know how far we'll come. I prepared some 40 sheets, and I think we'll be halfway at 45 minutes. And then I think we do just questions and do the rest the next time. Okay. So there it is. I hope everybody sees my screen. It was already immediately the second screen. It is a crash course in quantum physics. Why do I call it a crash course? Because it's rather short, but I have put everything I think that's essential in it, essential for your understanding why it is important. Quantum physics, its message is received in, say, between 1900 and 1920 by physicists like Bohr, Heisenberg, Max Planck, and others. After that time, its message is almost completely ignored. The first quantum physicists, they knew what was happening. And now around 1950, you couldn't ask the teacher, what does it mean? No, shut up and calculate. But I want to tell you, mind is primary and creates or manifests matter. That's what quantum physics says. And I'm going to tell you why. The best way to understand quantum physics is studying the double slit experiment. So we have to study that. I'm going to do that. Also, you have to use your imagination. Try to visualize what happens. And try to abandon your ideas about the material reality. So I'm going to show you the double slit experiment. And the first double slit experiment was done in 1800 by Mr. Thomas Young. He made 2 slits in a glass plate covered with soot and shone sunlight to it. And he got an amazing pattern on the backside of it. You can't understand this with the idea of light as rays or little particles. And Thomas Young knew already that there was someone, being in the time of Newton, a Dutchman, Christian Huygens, who already had said, light is a wave phenomenon. Nobody believed him, but Thomas Young made it really a fact. You can explain this pattern, what you see there behind the double slit, only when you see that light behaves like waves. Why not just two lines? Thomas Young made a description of what happened, presented it to the Royal Society. This is what happened after my two slits. What is the A and B are the two slits where light from outside comes in. Here comes light in from one single frequency to make it a little bit more easier to understand. And I'm sorry. You see that from those two slits, circular waves expand. And those circular waves, they have the same frequency and they overlap each other and they do something very peculiar and important. At certain spaces, at certain locations, they emphasize each other, and at other locations, they, you could say, destroy each other. So there are certain patterns, and there are almost like straight lines where there is almost no light, and there are also places where there's a lot of light. So you get those fringes. And since his experiment of Mr. Young, the fringes in a double slit experiment is a confirmation of wave behavior. So light is waves. Everybody accepted them. This little animation makes a lot better to understand. You see here on the right-hand side, the light waves coming on almost parallel, so they are coming from the sun, and the sun is far away, so the light waves will be almost parallel when they come in, and when they go to the through slits, they will, what they say, interfere with each other, and you see clearly the places, the locations where there's almost no movement of, well, the water. You can do this experiment also with water. We do that in high school experiments with a container of water and an overhead projector. You can do this experiment and it shows clearly this kind of patterns. Light is a wave phenomenon. But the question is, what is oscillating here? There is something that oscillates. And if there is something, if there are waves, then there should be a medium that is coherent that can support those waves. This was the reason why Huygens could not convince his contemporaries. And now Thomas Young demonstrated that light did not behave like little balls that Newton thought they were. But the question remained, what is oscillating here? A wave needs a coherent medium. So at that time, 1800, 1850, most physicists supposed an ephemeral medium, the ether. Ether would exist everywhere, even in dark places where you could lit a lamp, because then the light would also propagate there. So you needed ether in every dark place there, when you wanted to have light there. Well, that was, what is ether? And 1850, James clerk Maxwell found another solution of that problem. He found that electric fields that oscillate create oscillating magnetic fields. And oscillating magnetic fields create oscillating electric fields, and so on, and so on, and so on. So that's a wave. And we could calculate how fast these waves would propagate. And that's, well, I have to tell here in miles, 168,000 to 282 miles per second. And that's precisely the speed of light. So mystery was solved a little bit, they thought. Light is an electromagnetic phenomenon. I hope you see that what is an electric field, really? Or what is a magnetic field? It's something that happens in vacuum. So one supposed forces that could go through space unsupported by space itself. But anyhow, this is the presentation where they believed it should be. You see here the electric field, the blue is the blue oscillation, and the red oscillation is the magnetic field. This is what they call polarized light. The direction of the wave, the direction of the oscillation of the electric field is in one direction. What does a wave do when it starts? If you throw a little pebble in a pond, you get a circular wave. It extends like a circle in every direction. And the intensity of the wave, you could say the size of the wave, we become slower and slower as the wave extends. And it extends proportional to the distance to the source. But we have as light and even also sound that extends in 3 dimensions. So we have a spherical extending wave, and the intensity decreases inversely quadratic with the distance to the source. Try to remember that. So if you double the distance to light sources, the intensity will be reduced by a factor of 4. And if you go 3 times away, the intensity is reduced by a factor of 9. And this will be in conflict with what Max Planck discovers 50 years later. Try to remember this feature of electromagnetic radiation or light. 1900, with a little joke, Max Planck discovers why we do not get a tan from a hot stove. Everybody thinks it's normal to get a tan from sunlight, but if you try to get a tan from your CV radiator, it won't succeed. Why is that? Couldn't you sit before the hot stove long enough to get a tan? There is enough energy there. You should have a little bit, yeah, you should wait a little bit longer than on the beach. But that doesn't happen. So that's what Max Planck, it was not his question, but this is what I'm making of it. And Max Planck discovered that energy, the electromagnetic energy, is transferred in little small packets. He calls them quanta. And the energy of every light quantum is proportional to the frequency of the wave. Now is the electromagnetic frequency of a hot stove, that's infrared. That's still very fast, it's about 300 terahertz. And the electromagnetic frequency of ultraviolet light is 750 terahertz. So there should we see the difference why we do not get a 10 from the hot stove, but we get a 10 from the sun, from ultraviolet light. The energy of an infrared particle, Planck supposed light is particles, and the infrared particle is just 40% of an ultraviolet particle. Each infrared particle is harmless for our skin. And an ultraviolet particle has enough energy to harm our skin. So it produces 10. That's what we do. We harm our skin, so we get a nice tan. And now that's important. The energy of a particle, of a light particle, does not decrease with distance. So there we have a very hard conflict. We saw that the electromagnetic wave decreases its intensity with distance. And now we have small particles that do not decrease with the distance. Sorry. There is a collision in physics between the EM wave model and the quantum model. So you imagine what Planck discovered was not, well, his colleagues did not think it was real what he found there. He had to wait for his Nobel Prize for about 20 years before he got it. And then there were other problems. Rutherford discovers that matter consists of atoms, and atoms consist of positive nucleus surrounded, orbited by negative electrons, like this. This is a completely wrong model, yeah, but you see it everywhere, yeah. You see the electron surging there. The problem, this model has a big problem. This means oscillating charges. And they go round and round and round, and that's the oscillating charge. An oscillating charge radiates electromagnetic energy. And so the electron will lose its energy, and well, it ends upon the nucleus. And Rutherford found that an atom is, and I'm going to read it, 99.999999999996% empty space. If I give you numbers, it's not possible to see what this means. And I make often the comparison, if you're walking around in the dome of St. Peter in Rome, and you see a little fruit fly there in the dome. Well, the little fruit fly is the nucleus, and the dome of St. Peter, that's the electron shell. These are the, well, that are the, that's good comparison. Which means that if you would remove all empty space from a solid mass with the size of St. Peter's dome, you will have all that mass concentrated in the size of a little fruit fly. Okay, well, we can live with that. But electrons would lose their energy. And well, reality would look a little bit different if you realize that. Yeah? Every atom in the universe would shrink to a very small part of its size. This does not happen, says Bohr. Bohr found the reason why this doesn't happen. And he says nature allows only special discrete energy levels for each electron. An electron can have only certain energy levels and it cannot go lower. He didn't know why. He could not say what the reason why nature allowed only that, but he said it was an explanation also again that this contemporary said, okay, nice explanation, but you cannot explain why nature doesn't allow this. Anyhow, it could be the reason that we have real atoms with a lot of empty space in them. And it is not an interesting proposition, but the great question was, why were there only these special energy levels? And great discoveries in science arrive often by inspiration. Well, this is what Bohr supposed happened in the atom. Yeah? You see the electron circling in a certain orbit. It can only go in these two orbits in this animation. And if it goes from the high orbit to the low orbit, emits a little energy particle, we call that a photon. And when it receives a photon, when it receives a little bit energy, it goes into another orbit. And importantly, you see that it's immediate. So it's the animation, and the animation is correct in this. And the electron does not move a little bit lower and lower and lower and comes in a lower orbit. No, it is instantaneously from the changes between those orbits. But the big question is, why are only these orbits allowed? And de Broglie finds perhaps a good answer. And that's because Planck had already said, and Einstein has proved it, that waves are also particle-like. And de Broglie said, well, okay, it's perhaps also that particles are wave-like. The reverse is perhaps also possible. And if that's so, the electron will oscillate around the nucleus, and then you get standing waves. I'll show you. It's only a whole number of wavelengths will fit on the orbit for stable standing waves. You see here a wave. Yeah, well, you can count for yourself. Yeah? It's 1, 2, 3, 4 wavelengths fit in this orbit. and that's a standing wave. The electron is going around as a wave. It will meet when it's gone full circle, its tail, and it has to fit the tail. This is the only way it can happen. This is very, you can compare it with the waves on a string. Yeah. Well, okay, it was a bold proposition. De Broglie was, it was his promotion piece. And his promoter thought, well, this is so weird. I'm going to send his paper to Einstein. And Einstein sent it back and said, okay, now there's light in darkness. Perhaps this is a good solution. A few years later, this idea of de Broglie, it was a weird idea anyhow, was confirmed by experiments shooting electrons at crystal grids, and you got these kind of pictures, which means interference. I told you in the beginning that interference is a mark of wave behavior. So electrons show wave behavior. Well, okay, we have solved a little problem. Next problem comes around. Look at this. If an electron would behave like this, the hydrogen atom, for instance, that has one electron and one proton as nucleus, would be as flat as a dime. And it is not flat as a dime, it's more a little sphere as we see it. So how can this happen? Then comes Schreiber. The idea of de Broglie was a two-dimensional flat type of movement, thinking still about how planets revolve around the sun. The planet Earth revolves about the sun in a plane. It is not circling around the sun like an angry fly. It's an elliptical loop in a flat plane. So you would need a stack of hydrogen atoms to get something with 3 dimensions. Okay, how do you get a 3-dimensional wave and a 3-dimensional standing wave on top of that? That's quite a complicated question. And Schrödinger found an answer to that. That's happened often in science by a flash of inspiration during an extramarital sojourn. I don't know if this happened to many physicists, but anyhow, it's known that it's happened with Schrödinger. This wave extending, standing wave around the nucleus is explained most of the times as a probability wave. And that's important. Probabilities do matter, but are not matter. They are matter. Is this wave matter? Schrödinger thought it was matter. Schrödinger thought it was a spread out electron. Bohr couldn't convince Schrödinger of a probability wave. There is a little story about Schrödinger visiting Bohr in Copenhagen, and Bohr was known for arguing in the indeterminate. ignored until you were deaf. Yeah. So Schrödinger got enough that got sick and retired to his room. So Schrödinger was lying sick, feeling sick in his bed. What Bohr did was going visiting Schrödinger in his guest room and continuing the argument. Can you imagine the situation? Yeah. But anyhow, most of the physicists will agree that it is a probability wave. Anyhow, they treat it like that. But what is a probability wave? Think about that. Heisenberg found something else, fundamental uncertainty. It has much to do with the probability wave. I have to tell something about momentum of an object. That's the product of its mass and speed. And a good example is a biker of, say, 80 kilogram hitting you with a speed of 20 kilometers per hour. Hitting you has the same momentum as a big car of 1600 kilogram hitting you with a speed of 1 kilometer per hour. The impact is the same. You can, what they do is, sometimes I'm a little bit aphasic, then I can find a good word for it. I'm sorry for that. Yeah, but it's the momentum of an object is its mass times its velocity. And the Heisenberg uncertainty relation tells you that you cannot measure the speed and the position, the momentum and the position of an object with unlimited accuracy. If you measure the position of an electron with great accuracy, the speed will become reversely uncertain. But if you confine the electron to a very small location, like an atom, it will bounce in there with enormous speeds. And then a lot is said about, well, this is only on the atomic scale, this uncertainty. Some physicists started calculating when does this fundamental uncertainty come into our reality and into our macro reality. And they calculated when you take billiard balls and you have 5 or 6 collisions, the movement of the billiard balls after that will be fundamentally uncertain because of the Heisenberg uncertainty. In this way, Heisenberg's uncertainty comes into our macro domain. Well, this, for some people, this is giving you a headache. If I tell this to the people of the Academy of Spiritual Science, they look out the window or they hum a little bit and say, okay, I try to understand it, but it's too difficult for me. And well, in each geval, for every object, the fundamental uncertainty of Heisenberg is valid. Yeah? And this gives a little bit range for our free will. For instance, what is the origin of this uncertainty? Well, the mathematical description, the Schrödinger equation, yeah, of the position and the momentum of a quantum object, that is the Schrödinger wave function. Yeah, a wave is spread out unbounded phenomenon. Imagine a wave on the ocean. Where is the wave not? The wave is everywhere. The wave is on the entire ocean. You can see it, it's very small, but it's all, there is no boundary for a wave. So that's the origin of this uncertainty. And wave has no sharply defined boundaries. Well, this is a little joke. You are probably here. You simply cannot pinpoint the location of a wave, and that's the origin of the quantum uncertainty of Mr. Heisenberg. Now we have, some problems. I hope you remember that you can ascertain wave behavior by a double slit experiment. The double slit experiment reveals almost everything important in quantum physics experiments. If you see fringes on the screen after the double slit, then you are seeing wave behavior. Absolutely. What it is that is oscillating is uncertain. And because Mr. de Broglie has found that electrons behave like waves, Mr. Akio Tonomura did send electrons through a double split in 1989 at Hitachi. There he was working there on the fabrication of electron microscopes. So are we going to look at that? And he's sending them one by one. You can find this on YouTube if you look for that. But well, Mr. Tonomura, for this little film movie, it took 1.5 days. About say 60 hours to get this result, one electron by one. So he speeded up the movie sometimes, so we don't have to wait that time for the result. So, but imagine this. These are little hard balls, as we think they are, going through a double slit. And if we wait long enough, we see that they will come upon certain places and they will not land on other places. They prefer to land in these fringes. Electrons behave like waves, even when we send them one by one. So now I can imagine that you think, okay, most people imagine an electron like a little hard ball with a charge. How can a little hard ball go through 2 slits? That's a big question. But if we think about the wave, we can say it's a probability wave. What is a probability wave? Probability means that we have a probability of finding the particle when we observe at a certain location. That's all. But probabilities that oscillate are hard to understand. There are they again. Wave-particle collision. most physicists do not like the idea of a probability wave. They will agree that the quantum function of Schrödinger gives you the probability of measuring the presence of an object at a certain location with a certain speed, but they do not agree that the quantum wave is a probability wave. And why don't they agree? That because a probability is not a material something. This would mean, if you accept that the object you are an object, an electron, or whatever, what you're shooting, is not a material before measurement. Probabilities are not material things. And above that, the question becomes how a measurement manages to alter a wave of probabilities into a measured material object. This is a very strange transformation. You have a wave of probabilities. There is wave, suppose it's coherence. Now, well, a coherent probabilities are very strange. Probabilities are mind objects. They exist in our minds. That's what I think, not outside. I think it's 45 minutes. We are halfway. I think this is a good place to stop and say next time we go further. Yeah. But I think in the meantime you have a lot of questions, so go on. Listen, I'll try to answer them. I don't know everything, really not. Yeah, but I'll try. Anyhow, so this we'll go on with this next time.
Steve's saying science cannot ignore consciousness anymore. How so?
If you, well, I'll try. Anyhow, quantum physics can only be explained by this probability wave phenomenon. You cannot, and probabilities are expanding, and then suddenly you have the materialized object. But probability is a mind object, and that's where I make the connection. That's where I, in next slides, the second time, I'll tell you, I'll make it more approachable, in the sense that when we are going to look in the slits, so which slits, for instance, an electron went, its behavior changes. And what does my looking in the slit do with the electron? Why does it materialize in a different way when I'm going to look at where it went? So that's the connection with your consciousness. I think it's at the end always the observer that creates what is observed. So if this is not enough explanation, I hope the rest of my presentation next week will offer more answers.
Thanks, Paul. Lily asked, so is the wave not material until the measurement mark is made? Is the wave not material?
Well, probabilities are not material. That's a very simple answer, but that's the way it is. It's a probability. You cannot find a probability in your drawer or somewhere on your table. Yeah? a probability is a mind thing. If you buy a ticket at the lottery, you buy a probability. But the probability is just, it's nothing. It's not a thing. Yeah? It's not material. It can become material if the lottery pays out. But as long as as you didn't observe the object, it stays immaterial.
Thank you, Paul. Nicole says, better than any talk I got in college physics. So that's some nice feedback.
Thank you. Thank you.
Bill Rain says, thank you, Paul. Question. From this explanation, do you think that due to our lack of understanding of the probability wave, we can assume that quantum physics is only the beginning, and we will be able to prove eventually that the speed of light is not a limit?
Well, that's quite a leap in understanding. I think it can be. A probability wave is something really different from matter. And Einstein's relativity is only about matter, real matter. Probabilities are mind objects, and they are not bounded by the maximum speed of light. There's a little report I have read that, well, I have to think about my language now at the moment. There is an effect in quantum physics. I'm not going to speak about that, but that's the tunnel effect. Quantum objects can be found on the other side of an energy barrier, because the probability wave is not bound by the barrier. A wave is unbounded, you know. So at the other side of a barrier, the wave will be there also a little bit less, but so you can find the object at the other side of a boundary. And there was a physicist who said, well, okay, if a quantum object comes at the other side of the boundary, it should have done that almost instantaneous. So it will seemingly go faster than light. And this has been measured, and yes, it is so. Yeah. So particles going through a boundary, they cannot go with their little energy. Yeah, they go faster than light. This is already proved. Indeed, I think this will be, and the other side is quantum physics was, the meaning of quantum physics was suppressed in, say, time between, say, the 40s and the 70s. You couldn't ask about the meaning of quantum physics then, as you wanted to have a career in quantum physics. But now things are changing. Quantum physicists are finding that the information you can gather from an experiment influences the behavior of the particles you are studying. And they report it. So things are changing. And the number of physicists that is acknowledging that the observer, the mind of the observer, plays a huge role in the materializing of the object is growing. So matter is dependent upon our observing it. That's and we'll be going to see that, and we will going to see that what this means. Mind is primary.
Paul, we've got another 7 questions, so we're going to have to keep your responses a little bit briefer than that.
Okay, I'll try that.
I know it's hard. Lily asked, if the wave is material when the mark is made, does it remain material?
What if the wave is not material, and what does it mean when the wave becomes material? When we see the particle, hitting the screen, means the wave has become a particle, material. But before that, it was not material. What does it mean? Because that finally it's an observation. And sometimes I say, okay, probabilities are mind objects between 0 and 100%. And a wave hitting a screen and showing as a particle, then we have 100% probability. And we interpret 100% probability as matter. Perhaps matter is only an interpretation.
Interesting.
Yeah.
Tom asks, how do electrons behave like waves as they flow down a copper wire? Wouldn't they want to disperse from the wire?
Well, anyhow, you shouldn't imagine the copper wire as matter and the electrons as waves. That's not good. Yeah. Everything, as long as we don't observe matter, it's a probability wave. And the copper atoms in it are also probability waves. And the electrons flowing through the copper wire are also probability waves. And the probability waves, they act together. And that's superposition and entanglement. We'll come to that.
Kathy asks, how does probability wave relate to the souls in the next dimension?
I don't have a good answer to that.
I don't think anybody does, Kathy. I think we have to work on that one. And when Steve Fry has a similar question. How does quantum physics theory relate to the afterlife?
Well, there is a relation, I think, because it supposes it needs the mind of the observer for the materialization of the object. That's first sentence. If you need an observer with a mind to materialize reality. So it puts the mind primary. You cannot suppose that the mind is generated by the brain. For the brain is a matter. This would be division of matter producing a mind, and a mind producing matter again, or something like that. That's nonsense. Yeah? So mind is a primary thing, and that's what quantum physics says. And that's, well, if you believe that, then you can also suppose that your mind is not generated by your brain, and it will survive the death of the brain.
Thank you, Paul. Sally Taylor says, to everyone. I think it might be important to define consciousness or the observer. How do you define consciousness and the observer?
That's a very important question. What's the role of the observer? What is an observer? What is consciousness? And really, I don't know what conscious is. I know what it does. That's experiencing. Consciousness is something that has the ability to experience its ideas, its thoughts. The observer, if you have an experiment, if you see a paper with an experiment, describing the experiment, they describe everything. Only one thing is always left out, the observer. I'll come to that in the second part of the presentation, that you can see that the observer has a very important role in the way objects materialize. And the definition of an observer would take too long here, I think.
Okay. Christina says, probability in a lottery ticket or positive thinking is hope. So quanta are emotions? Question mark. Are quanta emotions?
Emotions? No, I don't think so. Emotions are quite another thing, and I think the discussion would take too long to clear this up. Yeah.
Okay.
I get confused a little bit by this question.
That's okay. Now, Bill Rain is looking at the relationship between physical mediumship and quantum physics, and he asks, how can you explain apports with quantum physics?
How can I explain what?
Apports.
Apport. Yes.
Apport, yes.
Okay. Well, I don't know if that's a good explanation, but I say, in short, every observation is a creation. Creation out of probability into matter. This means that we can do a lot more than we do at the moment. If the mind is powerful enough to create matter out of probability, it can, of course, transport matter over enormous distances. And that's what apports mostly are. So I think there's a connection.
Well, this is Cheryl has a related question. How can probability apply to telepathy and psychokinesis?
Psychokinesis would be about the same thing.
As apport.
As apport. Yeah, because we create reality from probabilities by the mind. Then you can almost do everything. We are somehow we don't do it because we don't believe we cannot do it. Yeah? We believe we are divided. And now to telepathy, at the end of my presentation, I can only explain how we see the world by assuming that we are all connected and that we are part of one mind, and that a lot about telepathy. Telepathy is also it is an instantaneous thing. Yeah, it does not depend on distance. It does not depend on time differences, and so we are all connected with each other through time and space. That's what quantum physics also implies.
I think that's the real takeaway, Paul. That's wonderful. That to state like that. Now, Marie asks, are prayers waveforms?
Well, perhaps. If probabilities are waveforms, then I think all our ideas are perhaps waveforms, and also our prayers. And that's, I think, what I sometimes encounter in NGE accounts or from spirits that tell something in seances. Everything is frequency, everything is oscillation, and our thoughts have a frequency, and I think that's, yeah, well, it's a little bit vague, but I think that's the direction we have to think.
Bill Rain says, consciousness is probably the probability wave energy from the source energy manipulated by the individual consciousness. That's really interesting. He's talking about individual consciousness and its relation to source energy.
Yeah. Well, this goes beyond me. Really, it goes beyond me. I don't know. I'm very well. I would like to know, but I think I'll get an answer to that after my death. Yeah.
The relationship between the individual.
How the relationship is possible? Well, that's a big question. How is it possible that I'm an individual, and I'm also part of source?
That's the big question. Thank you, Bill, for that.
That's a big question, and I don't have a good answer on that. Yeah,
I think we're all working on that one. Okay, now Steve Fryer has asked, why do you think that there are so many quantum physicists who still do not understand that consciousness is primary?
Because they are addicted to the material paradigm.
Very nicely said.
Yeah, if you don't want to see something, you don't see it.
Yes, that's exactly right.
Yes.
Beautiful.
I see it very often. Today I had a discussion with someone who really believed in consciousness created by the mind. We have no free will. And I saw he presented his arguments, and I thought, well, okay, I can see his arguments, and his arguments are bullshit. And if I try to explain it, his reactions are not logical anymore.
Exactly.
They lose the logic facility in wanting to keep their material vision. Yeah. For if they would use really logic, they would have to abandon materiality.
Oh, I love that quote. I must quote you on that one, Paul. That's
okay. Thank you.
Lisa's saying, are apports the realization of thought? Are they evidence of the force of thought?
Evidence of
the force of thought. That thought actually creates a force.
Yeah, I would rather say it's force of the mind. The mind creates thoughts, And I think, well, a lot of spiritual connections say that thoughts matter. Thoughts are more powerful than you think. I think in a sense, essential is a thought the same thing as the materialization as of an object. Both are thoughts. Perhaps, is that an answer? Perhaps.
I think so. And Christina has a similar question. Somewhere love comes into the equation. Is love, the force of love and the force of thought, is there any relationship? Where does love come in?
Then you drive me to speculation. Love, I think source, if I can give a name to it, or God, or whatever, source is love.
Right, that's good.
It's the same thing.
Same thing.
That's all there is. Yeah?
Now,
Love is expressing itself in thought, in humans, in animals, in earth, in matter. Okay.
Thank you, Gabe. Gabriel has a question. Has any scientist reached out to the former scientists who are now on the other side to see if they have a bigger understanding now?
I know Tesla is one who comes through, but I have not heard of other scientists like Bohr, Heisenberg, and Planck. And Planck was very convinced of matter is primary. Schrödinger, at the end of his career, said there's only one mind, yeah, in the universe. So the scientists, they were very
it would be very
what was happening.
Yes, it would be very interesting to see if any of the physicists are coming through mediums with a bigger understanding. Bill is.
Can I
sorry.
say something?
Yes.
I've never been in a seance, and it would be one of my questions.
It would indeed. Yes, exactly.
Yes, I would. Can Einstein come?
Well,
answer some questions.
It would be
please.
Wonderful, wouldn't it? Would be wonderful to see. Bill Rain says there are none so blind as those that will not see. I think we all agree with that one, Bill. Mike Jordan Riley says, thank you, Paul. I enjoyed your presentation. See you next week. Lee says, thank you, Paul. Second time we meet today. Bill Rain says, going back to the wave theory of the electron path, why is the amplification of odd waves better in EM communication? Bill, we might need you to clarify that.
Yeah, we can. I would almost say you can find me on the internet. I have a website. Perhaps we can put it in the chat, the address, the URL. I type it here.
Already there. Giles put it in already.
Giles put it in already, Paul.
Yeah.
It's in the chat window.
Okay. And you can connect to me there, and these kind of questions I have to think a lot about. I have to take some time to give a good answer about that.
That's fine.
I love real questions, and sometimes I don't have the time to answer them. So do it, please. Yeah, go to my website, find the contact page, and ask your question there.